Thanks, Jimmy. Hi, everybody. All right, let's just get started right away with evaluating CockroachDB and YugabyteDB. For context, some of this work, like Cockroach published a blog post about the architecture of Yugabyte and what they observed as performance, et cetera, et cetera. Like while we really thank them for the effort that they had put in, what we realized was they didn't really understand some of the things about how Yugabyte works. So we did like we started investigating how we would have run things at scale and across a different set of evaluation criteria, right? So this webinar is a result of that work. There is a corresponding blog post and a landing page, as Jimmy said, and all of this stuff will also be given to you in the form of slides, right? So, okay. So first off, a little bit of context. Cockroach and Yugabyte are both distributed SQL databases, right? And so that brings up the question, what is a distributed SQL database? A distributed SQL database is one that supports SQL capabilities, right? And like any database, how much it supports in terms of SQL capabilities depends on the database. And in addition to that, it is resilient to failures, which means if you're deployed in the cloud and you lose a node or a zone, it should be able to survive that failure automatically without manual intervention. It should be scalable, which means if you needed to expand the number of nodes that you have for processing power or storage, you should be able to do so by simply adding nodes. So it should be scalable or horizontally scalable. And it should be geographically distributed, which means you should be able to deploy the database in a multi-zone, multi-region fashion, right? So that's really what distributed SQL as an architecture for databases is about. Yugabyte and Cockroach are both distributed SQL databases, and so we'll start diving into the details here. Okay, so specifically, what is Yugabyte built for? What is the aim of Yugabyte, right? So Yugabyte is a distributed SQL database, and in addition to supporting all the things we looked at in the previous slide, Yugabyte supports the following other top-level design goals. It should be high performance. I mean, given that performance is either throughput or latency, you could kind of argue that as you add nodes, it would scale out. But one aspect of performance is how much throughput can you offer for a given set of cores, right? So it is built for high performance, which means for the same set of cores or a fixed number of cores, you will get a lot of throughput and low latency serving, right? The second thing is it's cloud native, which means it can run on Kubernetes, VMs, bare metal, etc. The third thing is it is 100% open source, the entire database, including all the enterprise features such as backups, encryption, security, etc., under the Apache 2.0 license, which is one of the most permissive licenses out there. Okay, let's go into the evaluation criteria, right? So what did we look at? And we're going to look at some of the architectural aspects on the side as we go through this journey. The things we looked at were what is the RDBMS feature set or the set of SQL features supported by both of these databases? What is the performance of these two databases as measured by YCSB? What is the performance and the operational characteristics at scale? What are some of the key architectural takeaways from observing these characteristics at scale, right? And at scale, and by scale in this case, we're not really expanding the cluster. We're putting a lot of data into a fixed set of nodes, which is a precursor to actually expanding the cluster, right? So one of the big reasons people choose distributed SQL databases is the ability to scale, which means they should be able to survive to a point where scalability is needed. And finally, we'll look at the licensing model. Okay, so let's get started with each of these, right? So firstly, RDBMS feature support. Both databases are Postgres wire protocol compatible, right? Like CockroachDB and YugabyteDB. But there are some subtle differences with respect to whether a database only speaks and understands the Postgres wire protocol versus whether it offers all the features that PostgreSQL actually has, right? So what we find is that Yugabyte actually reuses the PostgreSQL codebase, and we're going to build up a competitive list, right, as we go along, and this is just the first entry in that list. So it reuses the PostgreSQL codebase, while CockroachDB has rewritten the entire SQL layer in Go, right? Now, what we found, we actually started with the rewrite in C++, right? And what we found was that Postgres was so rich in terms of its feature set. After all, Postgres is developed over 20 plus years. that it was going to be near impossible to build all of these features by hand, right? So we reset about 4 to 5 months of effort, went back to the drawing board and said it's much better to reuse the PostgreSQL code base. Now, we're super happy we did that because you can just see that even though Yugabyte as a project started after Cockroach, we're able to support a number of relatively complex and advanced RDBMS features, right? And these include things like expression-based. I mean, it's just like a list here that we quickly put together. But expression-based indexes where you can actually declare what you want to index as an expression, or like partial indexes, table functions, stored procedures, a variety of built-ins and operators like across the board. There's a couple of examples there, but the completeness is always a hard thing to chase, right? And triggers, user-defined types, temporary tables, row-level security, column-level privileges, extensions that work at the query layer. We're working on foreign tables and the foreign data wrapper. So the list is really big, like of the things that Yugabyte actually benefits from reusing Postgres. What does this mean to the end developer? This means that people that are exploiting PostgreSQL to get their apps to perform the way they want can continue to exploit Yugabyte in a similar fashion with the promise of scalability, high availability, and geographic distribution. Okay, so the blog post by Cockroach Labs in return said that YugabyteDB uses PostgreSQL for the SQL optimization and a portion of the execution. But reusing PostgreSQL results in a monolithic SQL architecture. So this was the pushback that we got. However, this is not entirely accurate, and let's look at why. Right? The way we think of building a database like Yugabyte is to go in 3 phases, right? It's just simplifying the problem. These phases are not strictly sequential, they're overlapped, which means that different phases would have gone to different levels of completion, but all 3 are currently in progress, right? And that's how it works, because there's no use just building one layer and waiting to do the next. So how did we enhance PostgreSQL to a distributed SQL architecture? The first phase, and we look at a slide about each of these, right? The first phase was simply to get the SQL layer to run on a distributed store. And the result of only this phase would result in something that moves the data to a head node, right? So by a monolithic architecture, what Cockroach meant was all the data would have to be read out to the node that processes the query, irrespective of where they're stored. And that means something like, say, you wanted to do a count star of all the rows in the table, you'd have to bring all the rows in the table to a single head node and do the processing, right? If Yugabyte only did the first phase, that is a true statement. However, we did a second phase, or we are doing a second phase where we do pushdowns of some of these queries. So we can break these things apart and start pushing them down into nodes. And the third phase where you can actually enhance the optimizer to take into account table statistics and where data is located, and et cetera, right? So all 3 phases are in progress and at different levels of completion. Now let's look at each of these in a little more detail, right? What is phase 1? So what Yugabyte did, with Yugabyte, what we did was to take PostgreSQL, which is shown on the left. It has and let's kind of logically split a single node PostgreSQL RDBMS into 2 parts, right? An upper half where you have the query layer, which does parsing, analysis, rewrite, plan, and execute. And a lower half, which deals with the disk. So this would be things like the write-ahead log, wall writer, background flusher, vacuuming, so on and so forth. Now, when you move to a YugabyteDB architecture, we reuse the upper half with modifications, of course, made inside to appropriately work with a distributed document-based storage layer, which is the lower half of Yugabyte, called DocDB, right? So this gets your SQL layer to run on top of a distributed DB, and each node becomes stateless. The second phase of how we're building YugabyteDB is to start doing pushdowns. So you now have an execution plan for Postgres. So from Postgres, so you have an execution tree. You can start taking subtrees or sub operations from this execution tree and push them down to the appropriate nodes. So that requires identifying which nodes or tablets or shards of data these subtrees have to get pushed down to, and execute them at the lower layer, bring up the results to the query node, and then do the final processing in order to achieve what the end user said, right? So we have a number of pushdowns. You can find a lot of write-ups about what type of pushdowns we currently have in a bunch of blogs, right, on blog.yugabyte.com. Okay, the third phase is to actually enhance the PostgreSQL optimizer. Like even rewrite the query plan, and like, Postgres uses the Volcano model. What can we do there to really make it better for distributed like execution? So here, these require taking in a variety of things like, there's basic heuristics, table statistics based hints, geographic location based hints, rewriting the query plan, and so on and so forth, right? And so this is also in progress. So each of the three phases is simultaneously in progress and at different levels of completion. Okay, so now that we talked about, and so what is the result of these three, right? Like what this will let you do is actually push down a lot of the execution closer to where the data is and reduce the amount of data that's being sent to the query coordinator node. And the result of this is a truly distributed SQL database, right? So this is what underlies. So while on top, like the pushback was, this is a monolithic SQL, it's far from it. It's actually a distributed SQL execution engine. Okay, what are some of the advantages of reusing PostgreSQL, right? Like multiple times, I think in the Cockroach Labs post, there was this pushback that starting with PostgreSQL has led to a bunch of issues, right? But while that's not true, like here are some of the advantages, right? So firstly, we're able to support some of the most advanced RDBMS features. In fact, Yugabyte is probably the only horizontally scalable distributed SQL database that can support some of these advanced features like triggers and stored procedures and partial indexes and expression-based indexes and extensions and so on and so forth. But much more than that is not just supporting the advanced features. Like coming up with building some of these advanced features takes an incredible amount of time and effort, right? So you need a robust design. You need code that is battle tested like across like a variety of different deployments. You need that feedback to flow in and to mature the software. And you need great documentation to really think about and understand how it works, right? So the advantage that Yugabyte gets is a lot of this work is done by PostgreSQL. So reusing that has really, really yielded a lot of benefit, right? On a related note, it does keep the quality really high, right? So we're able to take a lot of the PostgreSQL regression unit tests and run them in the Yugabyte suite, right? So if you look at like some breakdowns on how much we test, like Yugabyte, like PostgreSQL, for example, has 192 regression files. We have about 60% of that, 114 of those. And about 68,000 lines of code that do unit tests, 33,000 of which have found their way into Yugabyte codebase, and 29,000 SQL statements that are being tested, about 15,000 of which are in the Yugabyte codebase. So just wanted to point out that moving this type of unit test suite into Yugabyte for like completely is something that we intend to do over time. And obviously, Yugabyte offers certain features that will work slightly differently or perhaps even in addition to what Postgres offers. So we are enhancing this to increase the overall coverage, but this forms a very great starting point. Okay, so enough about the RDBMS features. So let's just look at performance, right? And we'll keep this section quick. For the following reason, right? Like this set of comparisons are each run by the vendors, which is Cockroach Labs in their case for CockroachDB and Yugabyte in our case, with our own set of YCSB benchmarks, which are faithfully implemented according to the YCSB spec, but they are custom benchmarks, right? So they're custom implementations of the benchmark. So Cockroach Labs first reported in their blog post, like I think around November or December last year, that the Yugabyte 2.0, the SQL version that came out, which was just the first production version, had like poor SQL performance, right? And that Cockroach was performing a lot better, right? And so that's the gray bar. And they also reported with their own custom driver for YCSB that their performance was something. And we just like have put those two into this slide for context. Sorry. Yeah. Okay. So with the 2.1 version that went out, I think end of February, so it's not really a whole lot of time between the two, we were able to improve the performance really quickly to something that performed better than Cockroach in most of the workloads. And this is the YSQL or the Postgres compatible API, right? And the performance of the Postgres compatible API, the YSQL API is really increasing rapidly with every release. Note that like the YCQL API, which is Yugabyte's cloud query language API, has a much, much, much higher performance than any of these. And this is something that you could run even with the standard YCSB drivers and so on. Okay, so with Yugabyte's DocumentDB like core storage model, one thing to realize, like a couple of takeaways, is that both YSQL and YCQL are just query layers, like pretty much stateless query layers that run on the same document core, right? So the key things to take away from the Yugabyte side are that the YSQL perf dramatically increased from the 2.0 to the 2.1 version, and we just are expecting to make such similar jumps going forward. The YCQL performance is much, much higher than like both YSQL and CockroachDB. And over time, because it uses the same storage core, which implements transactions, which implements storage, lookups, and all of that, all of the harder parts of a query, we expect YSQL performance to start to match what YCQL will do, because both of those are like relatively stateless query layers in some sense. Okay, so here's some overall takeaways that we noticed while doing this exercise, right? Vendor-specific benchmarks are hard to run, right? Like, so if like Yugabyte has a suite of how to run YCSB and Cockroach has their own suite implemented in a different language. So Yugabyte's suite is in Java, Cockroach's suite is in Go. It makes it very difficult to figure out like, what did we just run? Is that the right thing to run? Is the database set up right? It becomes really hard. So that kind of puts out any ability to compare databases at all, right? Like period. The second issue that we noticed was that the benchmarks that are being run are just being run for 1 or 10 or 1 million rows by default by YCSB, or a lot of people just run them for 10 million rows. It's not representative of a real life workload, right? Like where you come to a distributed SQL database for larger amounts of data. So we decided to repeat these at scale, and we decided to keep them with the standard YCSB driver with the standard JDBC binding, right? So there's no difference in the benchmark we're going to use, just to eliminate all kinds of bias. Like for example, for Yugabyte, there is a workload which does short range scans, right? Like, and the unique architecture of Yugabyte is we're able to really mix hash and range sharding. I mean, and we've written a lot about this, and we expect that the YCSB workload E, which does short range scan, actually use a mix of hash and range, right? But then there might be a different equivalent in Cockroach, and understanding all this gets really hard. So we said, like, both for Yugabyte and for Cockroach, we're going to keep it the same. We're not going to allow any of these customizations. We're just going to use the standard JDBC binding to do this test. And we said, let's do these tests at a much larger scale, right? Like, and let's see what we observe then. Okay, so when actually we decided to do the performance at scale, we said we would do it for 1 billion rows, but we ran into issues loading data into Cockroach and so on and so forth. We'll talk about that in a subsequent section. But we said within a reasonable amount of time, which is like roughly in the 24 hours, like kind of time window, we were able to load 450 million rows into CockroachDB. So we said we're going to stick with that number. It's big enough and it's representative enough, right? So at 450 million rows, if you run YCSB benchmarks against the two databases, what do we see, right? So let's look at some of the benchmark details first and then go into the actual results. Now, if you're loading 450 million rows, it comes to about 1.3 terabytes of data total, like across the 3 nodes, right? And so we picked a 3-node cluster with a replication factor of 3. And there is 1.3 terabytes of data across the 3 nodes. Note that this includes the replication factor. So the actual data set is a third. The logical data set is a third of this. But with replication, it comes to 1.3 terabytes total. We wanted to do 1 billion rows because that would have put each node at 1 terabyte or the total at 3 terabytes. But however, this is good enough. Each node is a C5-4XL node on AWS. So it's 16 cores, and it has been mounted with 2 5 terabyte GP2 EBS SSDs. We used CockroachDB version 19.2.6, which was the GA version available at that time. And we only tested it with range sharding because hash sharding was not or maybe perhaps is still not generally available, right? Like when we did this test. And with YugabyteDB, we used version 2.1, and we used YSQL API only. We're not looking into the YCQL here. We've like looked at that in a previous section. And we're going to look at both range and hash sharding, right? Like, because one of the things that Cockroach had also said was range versus hash makes a lot of difference in performance. But like, I think we just decided to do it both ways. In the range case, it was a pre-split table. Dynamic splitting is right around the corner, so it's going to land like pretty soon and be generally available. But yeah, right now we did a pre-split range table and a pre-split hash table for Yugabyte. We use the default isolation levels for both databases. So that means Yugabyte supports snapshot and serializable isolation levels with snapshot as the default. So we're trying to keep the isolation level default very similar to what PostgreSQL does. CockroachDB only supports serializable, and hence that would be the default. Okay, so the first thing we noticed right off the bat was it took about 25 hours to load the data into CockroachDB, while with YugabyteDB using range, it was about 9 hours, and using hash, it was about 7 hours, right? So what we noticed with CockroachDB was, and you can see in these in this graph, which captures the runtime, right? Like for about the 25 hours or so, that it starts off like quite high, or relatively high at 12,000 inserts per second, but then tapers down to about 3.5 to 4,000 inserts per second, right? So there's a decline in the throughput. Now, in stark contrast, like Yugabyte's throughput like held steady, and you do see these jagged patterns, and we're going to talk about what those represent at a later point, right? Like, but however, if you just average out those jagged patterns, you're able to see that there's a relatively steady progress in terms of what the throughput is. Okay, so some of the things that we see from here, like we'd already seen PostgreSQL code-based reuse, and some of the things you see here are that like RocksDB enhancements and the fact that we're using C and C++, a single language code base, versus CockroachDB using a black box RocksDB and Go C++ interlanguage switch at the runtime would contribute to the appropriate performance. This is our guess based on what we understand. And again, we're going to dive into some more details on what are the architectural aspects, what are the changes inside RocksDB that yield to some of this. We're going to look at a few of this in the next section. Okay, so here are 3 of the workloads where we're putting out what is the YCSB result using the standard JDBC benchmark at 450 million rows, right? So if you look at the update heavy workload, and these are all throughput numbers. So we just picked 3 workloads. So workload A, which is a update heavy workload. So it does 50% selects and 50% updates on the 450 million rows. You see that Yugabyte is able to do 34,000 ops per second, while Cockroach is able to do 5,000. And like, you know, similarly for the reads, you find that Yugabyte is nearly 2x what Cockroach is doing in terms of operations per second. And which is workload C. It's a pure read, just a select workload. And workload F is a read modify write, where Yugabyte is able to do 21,000 and Cockroach is about a fifth, like at about 4.8K, right? So if you want to look at the entire breakdown across all the workloads and what it yields with respect to range and hash and what the differences are, all of those are in our blog. Like you can read it there. Okay. The second aspect, so on average though, across all the workloads, what we found was Yugabyte on average delivered a 3x higher throughput, right? If you look at the latencies, so with the 3x higher throughput, Yugabyte also was able to do 4.5x lower latency on average. And obviously each, depending on the workload access patterns, the range, like what the variance in latency between the 2 databases differs. So again, workload A was about 90 milliseconds for Cockroach and 15 milliseconds for Yugabyte. And similarly, there are numbers 8 and about 4.8 milliseconds for a pure select, and the read modify write was 89 versus 17, right? Again, 4.5x average. So what we noticed is, what we talked about here is overall the fact that we're able to do not only sustained writes, but higher throughput, lower latency that Yugabyte is able to sustain with YCSB at a much larger data set. Okay, So the next question that we logically wanted to ask was like, hey, how does the performance of each of these databases? So now we have the numbers that are in the 1 to 10 million rows range, and we have numbers that are in the 450 million rows range. So an interesting question to ask is to compare each database with itself, right? So how does the performance of each of these databases, so how does the performance of Yugabyte or Cockroach get affected when you go from a small data set to a large data set, right? And a large data set like 450 million rows is closer to being representative of what you'd probably see in the real world. Okay, so what we found, so this chart plots the drop in throughput, right? So what it says is like, the blue bar says what is the percentage drop that Cockroach experienced when you go from the small data set to 450 million rows, and the orange bar shows you the percentage drop in Yugabyte's throughput when you're scaling the data set size. So what you notice is that Cockroach drops like anywhere from 40 to 60%, depending on the workload, like each of the YCSB workloads, while Yugabyte is more in the 4 to 12%, something in that range, right? And similarly, if you're looking at, for example, the update latency, you see a similar increase in latency when you go from a smaller workload to a larger workload for Cockroach versus Yugabyte. You see that the increase in latency is also a lot lower for Yugabyte compared to Cockroach. So if you average out everything, what you find is that when going from smaller to larger data sets, Yugabyte's throughput drops by about 9%, while Cockroach's throughput drops by about 51% on average. And Yugabyte's latency goes up by 11%, while Cockroach's latency goes up by 180%, right? So this is the effect of data set sizes on the database. Now, there's a number of reasons why this could be happening, but here's another look at the problem, right? Like, so a lot of this could be playing even at the steady state. So here, this section, we're going to talk about, so we looked at performance, right, at scale. We looked at RDBMS feature set, we looked at performance at scale, and just the raw YCSB numbers reported by each of the vendors, what it looks like when you standardize the benchmark and go to really large data sets. Now we look at some of the architectural takeaways that we had observed while loading or attempting to load 1 billion rows into each of the databases. So when we tried to load 1 billion rows, because that represented a nice number, like it's about 1 terabyte per node of data, including the replication factor, or a 3 terabyte total data set across 3 nodes, right? Now, Yugabyte was able to successfully complete loading the data in 26 hours, while Cockroach failed to load this in a reasonable amount of time, because like YCSB kind of gives you a prediction on how long this would take. I think at the onset, it was like something in the, like a day and a half, but after 1 day, the throughput had dropped sufficiently low that the expected time to finish was like a further day or 2 out, right? And so because the throughput kept dropping over time, we couldn't really complete this exercise. So our next step was like, we had stopped it about a day later, and we said like, let's investigate why CockroachDB was not able to load this 1 billion rows in a day or even a day and a half, 2 days, sometime, right? It seemed to be a rolling estimate on how long it takes, because if the throughput keeps dropping, your estimated time to finish keeps increasing. So here's what we found first, right? Like, so again, once again, just to bring back the setup to everybody's mind, we had put 3 nodes, each node with 2 disks. Each disk was 5 terabytes of GP2 EBS. So it's it's a redundant SSD. So it's a mounted SSD drive. And this is a pretty standard setup for the AWS cloud. And a lot of our users use us in this fashion. So we didn't really think too much about this beforehand, right? Like, so the first thing we noticed was CockroachDB was using one disk much more than the other, and it wasn't really evenly dispersing data across the 2 disks, right? And our guess, like based on looking at their architecture, is that the CockroachDB's shards, right, which are called ranges, all get packed into a single RocksDB. And RocksDB has only uses a single RocksDB uses a single disk, right? Like they ask you to RAID stripe the disks or do something else at the lower half. These are like to the disks in order to be able to effectively leverage some of these. And this is in operational practice a pretty complicated setup, right? If you have to RAID stripe disks and so on in the cloud, at least. So with Yugabyte, we were able to see, so note that like in here, like what we are seeing here is that these are the two mounts that are like mounted on each of the nodes, and these are the three nodes. So if you just take one node, for example, it's got about 455 gigs on that node, which is a 5 terabyte disk. And you expect, if you add up the three guys, like 450 gigs or so, you'll get roughly 1.3 terabytes. And you see that one of the disks is actually just 400 megabytes, right? Now, in Yugabyte's case, you see that each of the nodes is roughly the same, like 450 gigs, but both of the disks have equal amount of data spread, right? And this has to do with Yugabyte's architecture and how it does sharding. And a Yugabyte shard is called a tablet, in contrast with a range. A fundamental difference between range and tablets, right? A tablet uses its own separate RocksDB, while a range, multiple ranges are stuffed into one RocksDB. They multiplexed into a single RocksDB, right? Now, there's a lot of work that we've done at the RocksDB layer, like in the DocDB storage, in order to allow multiple RocksDBs to coexist on a single node. Because if you have one RocksDB per tablet, and you can have like, hundreds of tablets or even thousands of tablets per node, then you would have that many RocksDBs running on that node. And so we've done a lot of work in order to global size the memory sizes, the mem stores, the compactions. A lot of work has gone into tuning and running multiple RocksDBs on a single node. Okay, so let's add that like ability to leverage disk. I mean, what we did not experiment with, or what was not clear, was, is it just a single table thing, multi-table thing? We did a couple of cursory experiments where we found that even creating subsequent tables had the same skew, but we didn't delve too much into that after a certain point. Okay, so issue number 2 that we had observed was that like the compactions had started shooting up as we started loading data. The compactions were starting to affect read performance, right? So right after loading the data, because it was a part of a script, we just ran the YCSB performance, and we saw that the performance was way low, even compared to what we expected from CockroachDB, right? So, so we observed that it was giving about 8,500 writes per second, or reads per second, sorry. And the latencies were much higher, right? Like you can see the P99 latencies displayed below. They go to about 4 seconds and then drop down to about, over 500 millis, right? So this is P99, but even the average latencies were higher. So we found that the performance was really poor, right? And it's not quite what we had expected. So what we found when we dug deeper was that as the data was being loaded, you see that the graph on top here shows you the number of RocksDB SSTable files. And SSTable file is a data file of RocksDB, right? As it keeps flushing data, it creates new files. So you see that the number of files keeps increasing. Now, there is a background process in RocksDB called compaction, which keeps reducing these number of files, right? So what this shows is that even though compactions are running, they're not quite able to keep up with the proliferation of files. So you see that a lot of data is like a lot of files are starting to accumulate. Now, if you have more files, it means when you do a read, you have to consult more files, right? So that means that the read amplification, or the number of internal reads the database has to do in order to read data, is actually increasing over time. Oh, right? So that means the read performance would be poorer because the database needs to read from more files, and the latencies would be higher. Now, in order to fix this, what did we have to do, right? We just had to wait for the compactions to catch up. So we said like, okay, let's stop all the writes, let's just wait. And the compactions ran from, it took about 6 hours for all of the data to get compacted. That's shown here, right? The number of compactions here spikes up. And you see that the number of SSTable files remains high. And as the compactions begin, they start dropping. And it then comes to a more reasonable level. And after that, the read amplification drops, and we were now able to get a lot better performance from CockroachDB. I believe, I don't have the numbers with me here, but we were able to get much better numbers as expected, right? But now with YugabyteDB, the performance actually still holds right after the compaction, right? And that's because Yugabyte does its best to keep compactions caught up with the write load, and we'll look at why that is the case in the next issue. But we just put down here that compactions are tuned for performance in the case of Yugabyte, whereas they could impact performance in the case of CockroachDB, depending on your setup, right? Now, if you go into why are the compactions not able to keep up, right? Now, this happens because the database is not able to backpressure, right? So this becomes a scenario where the database is under stress because the disk becomes a bottleneck. If you as folks may already know, there is a limit on the number of IOPS a GP2 SSD has, EBS SSD has, and this is just the way it is in the cloud, right? So the disk could become a bottleneck, especially when you're having a lot of writes. And the issue is that the database can no longer keep up the compactions with the writes. And that means the database would need to backpressure the client to rate limit the amount of data it takes in. And this is a scenario that happens pretty often, right? Because you could have bursty behavior, you could have slower disks, and etc. So in this case, CockroachDB goes into a mode where the reads are severely penalized, right? Because you just build up all these files. Now, what does Yugabyte do, right? Like we said, we would revisit these spikes and drops. So there were cases when we were loading like 1 billion rows when Yugabyte couldn't keep up with the writes as well, right? Like, I mean, if the disks are bottlenecked, the disks are bottlenecked. So what we found was that to ensure good read performance, the database backpressures, like, and these are features we had specifically built like to address various real world scenarios. Yugabyte applies backpressure to the writes, which means you notice here that there's a period where the number of writes actually drops quite a bit, and there's frequent periods of drops every now and then, right? So that is the database actually telling the client that I cannot take any more writes, keep it like much lower than what I can do. And in that window, you actually see that the compactions have completely taken over and they're making sure they're caught up so that the read performance is always good. Okay, so we just put down the fact that, you know, there's back pressure when overloaded and there's no back pressure. So these are just like some of the architectural aspects that we had drilled down on. Obviously, you know, had we loaded like 1 billion rows, we would have liked to do more. But anyways, this was interesting for us also to look at like how different databases evolve differently with respect to the choices they make. In any case, another aspect in evaluating the two databases is the licensing model. I think it's like this is also present in one of our blog posts. It's just an image from that blog post. I think note here that I think what is the rightmost column shows you what is Yugabyte's licensing model. You see that the core database as well as the enterprise features in the core database are both Apache 2.0. Around the middle of last year, we switched from a closed core. So we had our enterprise features as a proprietary license to a completely Apache 2.0 license, right? This is because a lot of people kept asking us, hey, if you folks are trying to be as powerful and capable as a PostgreSQL, we would like it if you folks are as open in the open source side as PostgreSQL as well. And so we decided that, like, you know, our enterprises are finding enough value from our management software that the commercial side of the business is not going to get affected, and it would be a really good move to open source the whole database, which we did. Note that like this, the second column here talks about what Cockroach Labs, their licensing model is. So I think originally Cockroach had their enterprise features off the core database as a closed license, like it's a source available license. I think it's Cockroach Community License. But their core also moved from Apache 2.0 to BSL, which is really not an open source license, right? If you go by the OSI standards. So Cockroach continues to claim that they're open source as a database, but yeah, like it gets difficult, right? Like when you obviously the intent is to prevent cloud providers from running software, which I guess none of us want, but because we all want to make money on the commercial side. But in the spirit of open source, competition is a healthy thing. It keeps the database honest, the database vendors making a lot more good software for the world. And it's a lot easier for enterprises to decide when to use it in production or not, right? Like, so clauses which say you cannot run the database as a service if you're monetizing make it very difficult even for legitimate enterprises to figure out if they can or cannot run the database in production. So yeah, so this is just a screenshot from their own website which says that. So that's all. That's all I had. Let's like we're an open source community. We love stars. Give us a GitHub star. Join our community on Slack. But we will now open up for questions. And I see there's a couple of questions.